we help mitigate and try to prevent further climate change across the globe. And so if you take a look at kind of where the current greenhouse gas emissions come from different parts of human society, you can see that transportation and electricity make up a huge fraction of it. So you might also say, why not go after industry or agriculture? The answer is trying to eliminate greenhouse gas emissions from those sectors can be a lot more difficult. So if we can go in and make it so transportation and electricity are using clean energy or any kind of energy source that doesn't release greenhouse gas emissions or carbon dioxide, we'll have a really good step forward towards trying to mitigate climate change. So, all that being said, how do I propose that we are going to decarbonize transportation? It's simple. Nuclear-powered cars and nuclear-powered planes. This, of course, is a complete joke, but these were two things that were actually proposed in the 1950s. On the left, you've got the Ford Nucleon. It was your family sedan powered by a nuclear reactor that'd be good for 5,000 miles. On the right, you've got the Convair Peacemaker, which was an airplane that was actually powered by a nuclear reactor in its belly that could run for years at a time, essentially like a nuclear submarine, only limited by keeping the crew fed and well hydrated while up in the air. Fun fact, the Nucleon was never built, it was just a concept car, but the Convair Peacemaker was actually flown. They never hooked the nuclear reactor to the engines, but they did fly with a nuclear reactor in the belly of the plane producing power for hundreds and thousands of test flight hours. But that being said, how are we actually going to decarbonize transportation? It's going to be batteries and it's going to be electricity. And so you can see now, if we're really trying to take a big bite out of global climate change by transitioning to clean energy, it's going to be about how can we decarbonize and make clean electricity for the grid. So one of the things to keep in mind is that decarbonizing how we make electricity is going to be a huge, huge task. So right now, or in 2016, this is where we got our electricity from in Massachusetts. And you can see about 75% of it is coal, oil, and natural gas. Things that are going to release a lot of carbon dioxide and greenhouse gas emissions in the atmosphere. Only a small chunk of it is solar, wind, hydro, and nuclear, power sources that aren't going to be releasing greenhouse gas emissions and carbon. So the question is, if we want to actually try to get a decarbonized grid and get clean electricity for both residential, industrial, and transportation, what do? So it's going to be some combination of new nuclear, new solar and wind, a combination of the three of those, plus energy storage. And this ends up being a huge thing. For different types of power, you really, especially solar and wind, they don't necessarily produce power when you need it. So it's all about how you can store the electricity and then use it when it's being demanded. So if middle of the night, if you want to go ahead and turn on your lights, you need to make sure that there was some power source producing power at that moment. So it's either going to be something that can produce power at any time, like nuclear, or it's going to be something like solar or wind paired up with batteries. So a lot of times people will say, can we do it with solar and wind alone? And it's a great goal, but it's important to keep in mind that it requires a huge scale up in the way we currently look at electricity. So to give a quick example and a quick real world example, I went ahead and said, how do we produce electricity in all of New England on this day 1 year ago? So on June 2nd, 2007, you can see on the plot on the left where we, how much electricity we used and how much of it we got from solar and wind. So you can see in the middle of the night, so this is midnight on the left-hand side, people aren't using a lot of electricity in the middle of the night, and then as people start to wake up in the morning, the amount of electricity we used ramped up, stayed relatively high through the middle of the day, and came down at night. Down at the very bottom here, you can see how much solar and wind we made in all of New England. So you'd say, okay, let's go ahead and scale this up. What would that look like? So if you wanted to have enough solar power and enough wind power to power all of New England on this day last year, you would have needed to have 28 times the number of solar wind farms that we currently have installed and 112 times the number of solar panels that we currently have installed in New England. And while this is doable, it's a huge task. And if we're really concerned about decarbonization, these are the kind of barriers that we have to overcome in areas, especially like New England, where we don't necessarily have great solar resources. One other thing to note is that there's a bit of a mismatch here between when we were using electricity and when it was being produced last year. So you can see we had a lot of wind power in the middle of the night. It dropped down a little bit during the day and a little bit at night as well. And the solar, not surprisingly, we had no solar in the middle of the night. Ramped up a little bit right about 6 a.m., peaked up a little bit around noon. You can see it might have been a bit of a cloudy day, so it was kind of jumping in and out on what the production levels were, and it came down at night. The problem with that is that if we're talking about storage, if we're talking about making sure that you have electricity available when you need it, it's all about trying to match up that supply curve in purple with the demand curve in black. So in this case, if we combine the solar and wind and overlaid it on the demand curve, in red it shows you the areas where we would actually need to have battery power available, or in battery banks to store up all that extra solar and wind power and dispatch it throughout the day. So, before I give you the number of how much battery power you'd actually needed in New England on this day last year, let me give you a little bit of context. So between 2015 and 2018, in the entirety of the United States, we installed 500 megawatt hours of grid-scale storage batteries. To give you an idea, this is one of the Tesla battery stations they recently installed out in California. It's about 40 or 50 megawatt hours. For this day last year in New England, we would have needed 20,000 megawatt hours of battery storage. So 40 times the current national battery storage installed in just New England for one day in the summer when, let's face it, New England, we actually have pretty good sunlight up here during the summer. Middle of winter, that number is going to change a lot too. So the tasks that we're actually looking at, if we're just doing solar and wind with battery storage, is absolutely huge. It's not something that we can't overcome, but it certainly is a big challenge. What I want to propose is that if you actually look at a grid where you look at solar, wind, and nuclear, another low-carbon clean energy source that's not producing any kind of greenhouse gas emissions or carbon dioxide on the scale of natural gas or coal, it could help try to balance this out. So on the left-hand side here, you can see that same supply and demand curve we were looking at earlier. And so on the right, let's go ahead and say, let's say we put in some nuclear power in this mix as well. So nuclear power is a bit unique in the fact that you can actually change its power levels, and it's not based on whether the wind's shining, or the wind is blowing, or the sun is shining. So in this case, let's say we had a nuclear power plant that we could raise its power level a little bit in the morning, right when people are starting to wake up and there's that big increase in demand, and then right in the middle of right in the evening, right as the sun is starting to set, we'll ramp the nuclear power plant up, leave it up high for a little bit, and then ramp it down as everyone's going to bed. What you actually see is that the net effect of that on the grid is something where now our combined supply curve of solar, wind, and nuclear actually starts to match the demand curve that we have without the need for huge amounts of battery storage. And in this just particular analysis I ran, when you added that type of nuclear in, it reduced the amount of battery storage you needed by 66%. And this is just one possible combination of how much solar, how much nuclear, how much wind, how much batteries. And then in some grids, you'd also have things like natural gas that can provide other benefits to the grid. But really what I'm trying to get across is that trying to decarbonize with solar, wind, and batteries alone is going to be a huge, huge task. And if we're really, really concerned about fighting climate change, nuclear is a really interesting tool that gives you a little bit more flexibility in how you want to design your electrical system. So hopefully I've convinced you that, okay, maybe nuclear power has some benefits. So let's talk about what some of this new nuclear actually is. So this is one of the best examples I always like to talk about in my department. Nuclear power is just a really, really fancy, complicated way of boiling water. At the end of the day, we're just making heat and we're boiling water. So I assume hopefully most of you have a tea kettle like this at home. What we're using in a tea kettle is we use chemical reactions, the flame underneath the tea kettle, to boil the water inside the kettle. In a nuclear reactor, what we do is heat from nuclear reactions where we're actually splitting or joining together atoms that releases heat, and we use that to boil the water. So at the end of the day, just a fancy way to boil water. So for anyone that maybe hasn't taken quantum mechanics or nuclear physics in a few years, we're going to do a quick little review of atomic structures. So this is an atom. It's a nice simple combination of protons, neutrons, and electrons. So the protons and neutrons sit right here in the nucleus, and the electrons orbit around in a cloud essentially around the nucleus. So normally when you talk about electricity or you talk about chemical reactions, it's all about how these electrons are actually interacting with different atoms. When you talk about nuclear power, what we're really concerned about is the enormous amount of energy that's stored here in the nucleus, either by combining nucleuses or by splitting them apart. So the first type, when we're talking about splitting apart nucleuses, is fission, where you're actually taking a large atom and you're breaking its nucleus apart. And when you break it apart, it releases an enormous amount of energy. So in this case, what you do is we take one of those little neutrons, we shoot it at the nucleus of a big atom. It causes it to become unstable, and it breaks apart. And when it breaks apart, it does a couple of things. One, it releases what are called fission products, so you get two kind of big chunks of that original atom. You get a few more neutrons that come out, and these can be really good for sustaining a chain reaction. You can imagine if one of these neutrons went off and split another nucleus, you could get a self-sustaining chain reaction. And it also releases energy. And it's really important to remember the amount of energy that this releases. So this right here, you guys can probably barely see it in my hand. This is about the size of a uranium fuel pellet inside of a nuclear reactor. It's maybe half a centimeter in diameter, about a centimeter high. This little fuel pellet has the same energy as 1 ton of coal or 3 55-gallon drums of oil, all in this tiny little pellet. And it's because you can release so much energy by actually splitting these atoms apart. So it's a very energy-dense source. When you talk about fusion, this is the other side. Instead of taking a big atom and splitting it apart, what we're doing is we're taking 2 smaller atoms and forcing them together at a very high temperature and very high pressure. And when we do that, we get a little helium atom that pops out, another neutron, and then again, a lot of energy. So everyone here should be familiar with fusion energy in at least one way, because that's what actually powers the sun. The sun is just the world's, or the solar system's largest fusion reactor, and something that occurs naturally. So when you start talking about fusion, it's how can we try to recreate the sun on Earth and capture and harness that energy. So when we talk about new nuclear, really what we're talking about is trying to find new ways to try to harness this heat and boil water. So what are the cheaper, more convenient, and safer ways to do this? So there are a lot of different variations. Sometimes it's looking at smaller reactors, reactors that are safer, reactors for different applications, or even reactors that make their own fuel. So let's go ahead and hit a couple of the ones that they're actually actively designing today, and companies that are trying to commercialize these different designs. So the first one is X-energy. It's a helium gas reactor. So the big idea behind X-energy is they want a reactor that could never melt down, that would have absolutely zero safety risk. So what they did is they took a small little pinprick of uranium and they cover it in different layers of carbon and ceramic materials. And then they take that tiny little ball of uranium and ceramics and they throw it into a large ball of graphite. And then the nuclear reactor is actually just made up of thousands and millions of these little balls stacked into a giant column. And the advantage of a reactor like this is that you've got so many different layers that protect the uranium fuel and any fission products that are made afterwards that might be radioactive, that even under any accident condition, no radioactivity can be released. So the idea is of a reactor like this, it completely eliminates the possibility of a nuclear meltdown, and some of the things that people and engineers are concerned about when you talk about the safety of nuclear power. So this is one design that's actually currently being developed over in Maryland. There's a company working X-energy. Another design is Oklo, and this is actually a company that's been founded by 2 MIT alums, and they're designing something called microreactors. And this is a kind of a really cool concept. If you ever start looking at remote generation of electricity, you've got a small Arctic village, you've got a small village that's not really going to be connected to the grid. A lot of the times they're going to be dependent on getting their fuel shipped in for diesel generators. So this is going to be fuel brought in by plane, by boat, by truck, and they're producing all their electricity generally with pretty dirty diesel generators. So the company Oklo said, well, what happens if we could replace that with a small nuclear reactor? Instead of using a nuclear reactor that powers 1 million homes, what if we design a nuclear reactor that could power 100 homes? So what Oklo is proposing and currently developing is small microreactors for remote applications. So the idea is you just put a small nuclear reactor, something that can be run by 1 or 2 people. It's a very simplified, very automated design, and that could actually stay in a small Arctic village for decades at a time without needing any kind of service or refueling. So it's an interesting proposed approach of a new way of doing nuclear. Another design that's pretty interesting is the TerraPower design out of Seattle. So this is a design that's actually being funded by Bill Gates, and it's the idea of designing a nuclear reactor that makes its own fuel. So it gets a little bit into the weeds of how do the nuclear reactions work out. But imagine a car where you could put in a little bit of gasoline to start and then just keep refilling the tank with water. And as the car ran, it turned the water right into gasoline. That's essentially what the TerraPower reactor does. It takes a small amount of fuel in the very beginning, and then over time through a series of different nuclear reactions actually turns material that wasn't usable for fuel and turns it into fuel and uses it. So it actually will run on one solid core of fuel for 60 years without needing to be refueled. So it's a really interesting way of kind of harnessing some interesting physics tricks and turning it into a reactor that will produce a lot less waste and produces its own fuel. So the final design I'm going to talk about, and this is a really exciting one that's just come out of MIT in about the last 6 months, is Commonwealth fusion systems. And so we talked, all the reactors up till now have been fission reactors. We've been taking big, heavy uranium atoms, splitting them apart and releasing electricity, or releasing heat. What Commonwealth fusion systems does is they actually take those 2 light atoms and try to push them together and make fusion. So what their design is is they're developing methods to actually hold these plasmas that can be at hundreds of millions of degrees and hold them for long enough periods of time to actually produce electricity. Scientists have been able to do this for small periods of time in the past, but with new magnet technologies, the people at Spark are developing the technologies and the exact designs that'll let them do this and actually produce commercial power with it. So it's a really interesting startup that just came out of MIT in about the last 3 or 4 months. And their goal is to actually have design going, their first design in 7 years and a commercial offering in 15 years. So there's a lot of excitement and a lot of really cool work that's being done right now at MIT on this. So I really want to just leave you guys with the future of nuclear really is here today. There are a lot of companies doing lots of really interesting work. And the important thing is that this can all really help contribute to us fighting climate change. If we are really concerned about climate change being an existential threat, we need every tool available. Solar and wind and battery storage are great, but if we have a tool like nuclear that lets us produce clean energy, why not explore it? Why not try to use it? And a lot of the different technologies that are being developed are really going to be versatile in different regions of the world, different areas of the country, and in different situations. And so these are all technologies that are currently being developed and hopefully have a lot of promise. Thank you.
So we're going to switch